The first challenge is how can you produce materials without heat and pressure using organic components, all while producing minimal waste and pollution, which is exactly the opposite of how we manufacture things now. We heat things, we beat things, and we treat things to make this chair, to make computers, to make houses, homes. So but nature doesn't do this. So they are able to make these really fancy materials at just regular outside temperature, at regular pressure, and using just maybe 20 elements at the most out of the periodic table. Of course, probably the most famous example is spider silk. And yes, I know spiders are not insects, but entomologists are happy to talk about them. Spider silk is very strong, it's insoluble. Even when it rains, it oftentimes just hangs on. It's continuous, thin, it can stretch a little bit, it's lightweight, and it is produced at ambient temperature and atmospheric pressure with just a few components, just a few elements. How do they do this? Fundamentally, spinning of silk is a phase change. Here's the abdomen of a spider. In it are the components that are usually in a liquid form, and as it comes out of what's called the spinneret, it becomes a solid. So there's already a phase change that happens at ambient temperature. There's basically two different protein phases. Over here it's more dimers, which are just two parts to a protein, and then when it comes out, it's an oligo protein, a long, stretched out protein made out of all these dimers. There's also this it happens due to a chemical reaction. There's a shift in the chemical composition, and it happens at a different pH that causes this thread to form. And again, this all happens right here in the silk gland and in the spinnerets, which is not, these are ectotherms, these are cold-blooded animals, so this is pretty much just ambient temperature. And here you see these, there may be multiple spinnerets on one spider's body, and then the silk comes out and makes one big, thick thread. Now, the application of this is still in the beginning stages. Researchers really want to make silk and make it exactly like spiders make it, because it is so strong and so yet flexible. So Andreas Bausch and Thomas Scheibel at the University of Munich and the University of Bayreuth, they have come up with this. This is at a very small scale. Two components come together, chemical components come together, and they do form a thread, but they're not quite there yet. So these two different proteins flow along the tubes. The proteins are exposed to a salt solution, which then changes the pH a little bit. And then these proteins aggregate into little spheres, so already you see a little bit of a phase change. And then there's this sudden jump in acidity and change in pH. And then they break open these spheres, and then the proteins that were in these spheres stick together and form chains. And they can, by changing the speed at which the proteins go across, they can make into long fibers. But it's obvious when you look under a microscope at this thread that it's very grainy and that it's probably not as strong as the real thing. But this is how engineers are thinking about making another material that's really strong based on silk by actually using the same principles that the spider uses, but not heating it excessively, not using too many strange too many chemicals, just what the insect does. So why is this so importance? Well, there's lots of applications for this. Surgical stitching, for instance, using material that is, may not be rejected as easily. It has also been shown that you can use spider silk for the regrowth of damaged nerves. Then there's always the, and pardon the pun, the silver bullet. Engineers have always hoped to come up with a nice or bulletproof armor based on this strong material that silk is, very much like Kevlar, but even better, to make armor for troops. And then there's also the application of encapsulating drugs. To get drugs to the poorest people in the country, in the world, will require vaccines to be transported from one place to the other, and some of these places can be really hot, and they may not have refrigeration. So being able to encapsulate it, just put the vaccine in the glove compartment and move it to where the people are, would be very helpful. So hopefully spider silk or materials based on spider silk will help with that. Okay, the next challenge we'll discuss is how creating a multifunctional surface material without contamination of the environment, and making a material that we can use, maybe because it is self-cleaning, or maybe because it has a color that we really want, maybe by materials that are solar collectors and at the same time self-cleaning, or we're also really in need of better photonic materials. These are materials that are the next step after, I can't think of the name right now, materials that we will need. So, for instance, the inspiration are in insects. Oftentimes, insects create color with pigments, but already there, when we're talking about pigments, we're oftentimes talking about contamination. When we put pigments in things, in food, for instance, probably not the best thing. So it turns out that oftentimes insects also make colors by using chitin, which is the material that they use for their exoskeleton, by changing the way it is positioned. And this is called structural color. You can create structural color just by the way the light reflects off of the chitin that is perceived in a certain way. And not by using pigments, but just by changing the surface. So you can come up with really subtle coloration as a result of diffraction, or you can also have strong photonic effects due to layering. We'll talk about that.